So, good morning, everyone, and welcome to the final day of the Para 21. I am Gaurav Khare, and I will moderate this session along with my co-host, Mr. Chamalal Devangan. So, as usual, if you have any questions during the talk, please don't raise during the talk, but post it into the chat box so that after the talk we can take them. Now, without taking much of your time, permit us to begin the session with a talk on protection solution of the distributed energy resources and the microgrid operation by Professor Mukesh Nagpal. So please allow me to introduce Professor Nagpal. So Professor Nagpal is a principal engineer at BC Hydro, a senior member and a distinguished lecturer of the IEEE Society, an adjunct professor at the University of British Columbia, a professional engineer in the province of British Columbia, and a fellow of Engineers Canada. He has about 34 years of experience in the electricity utility research and the power system production. He has published approximately 50 technical papers with a notable contribution to the economics, safe and reliable integration of renewables to the electric grid. Dr. Nagpal is a recipient of 2021 IEEE Ramkumar Family Renewable Energy Excellence Award for the protection solution facilitating the grid integration of renewable resources. In 2016, he received the highest engineering order of the British Columbia R.A. McLachlan Memorial Award for exceptional leadership in the developing practical ways to connect renewable to the grid and improve utility power system in the industry. So it's a pleasure that you have accepted our invitation and spared some of the time from your busy schedule to enlighten us by your knowledgeable words. So on the behalf of whole Para 21 team, I would like to welcome you. Now I request Professor Nagpal to deliver his talk. Over to you, sir.
And thank you very kind, Gaurav, for introducing me. And I'd like to thank everyone and my sincere apology for mixing up time. It should not be I feel embarrassed about it. And so please accept my sincere apology. In fact, I had planned it for tomorrow, telling my wife, I wanted to have dinner early and call my friend if there was any IT problem, but looks like there's no IT problem. So I'm late, but still we managed. At least there's no IT issue here, so I can begin my talk. So what I'm going to talk to you is protection solutions of distributed energy resources and microgrids. And the topics of this tutorial, because there was a time limitation of around an hour, I limited my topic to protection issues associated with distribution energy resource connected to utility distribution systems and microgrids formed by them. What I'm trying to say, the scope of this presentation I've limited to electric distribution systems and microgrid forms in distribution system. As you know, distributed energy resources can be connected to transmission systems, and microgrids formed by them are not included in this presentation. You'll find few editorial mistakes on my presentation. I was to work on them tomorrow morning to fix them up. As you hope, thinking my presentation is tomorrow, so I do apologize for some of the editorial errors in my slides. I just didn't get time. I was intending to do them tomorrow, so please accept my apologies for that too. So my presentation is in 4 modules. And the module first is what I'm going to talk about, distribution system resources, or the resources, distribution energy resources connected to the distribution system. How they are creating microgrid opportunities. While they are creating microgrid opportunities, they are creating new protection challenges. That's what I'm going to talk about in the first module. The second module is how to overcome those protection challenges of DR. What I will specifically will talk about a 2-to-1 suicide rule, which my company has pioneered. Actually, it is published in an IEEE paper by myself and my co-authors or my colleagues. And it is also now a part of 1547 IEEE standard. Not the same rule exactly, slightly different rule, but the foundation of the rule is pretty much similar. So what I'll talk about 2-to-1 suicide rule, how this is helping or it is simplifying or optimizing protection solutions for DR connections. Then, once we have DRs, how we can make some incremental changes to make them work like microgrid. And what I'm going to do is going to present an example of a microgrid from my utility. I have two examples actually, and my examples are in the module 3 and 4. I'm going to present you module first, 4, and the module 3. That was my intent to do tomorrow, is to solve the module 3 and 4 to give you a better idea about what I was going to talk. So I'm going to jump to after module 2 to module 4 and then come back to module 3. Okay. There are resources to my tutorial, and they are listed in this slide, which you can do if you feel like for further reading. You can get these resources, these two papers, particularly the two papers. Third paper is still yet to be submitted. It is finished. The third paper is finished. We are just looking to submit that paper right now. So the first two papers are already available in in IEEE or website. You can retrieve them, and if you want to do further reading about what I'm presenting, you'll find in these publications. So before we get into distributed energy resources, let's look at I'm just going to get my left pointer here. What I'm going to talk about, what is a distributed energy resources? What do you mean by that? Traditionally, electric power system had hierarchical grid nature, a vertical integrated utility. There was a generation, there was a transmission and distribution. The electricity produced at a centralized large generating station. The location of generating station decided based on many factors. Where is the resources? For example, in this case, there is a potential for hydroelectric generation, and that resource or that location of generating station was always or not necessarily near the load centers. More often, centralized generating stations were located often far away from load centers. So the electricity had to be transferred on a high voltage transmission system. So electricity generated, stepped up, sent over high voltage transmission system. Then maybe a sub-transmission system, like this could be 500 kV, this could be 230 kV sub-transmission system. Then at the end, when the electricity came to the lowest voltage, which is called distribution voltage, in my utility, it is 25 kV or 12 kV voltage. It is stepped down further from sub-transmission level, which is in my utility is about 230 kV to 66 kV, or 130 to 66 kV. 230 we still call transmission in my company. So from 230 transmission to 166 kV, we bring it down to 25 kV or 12 kV, and then send the electricity to your homes. And these electricities are sent to the home. Again, near the home, then you'll find, at least in North America, you'll find it is a 4-wire. 4-wire means 3 phases, A, B, C, and a neutral wire is the 4th wire. 4-wire multi-grounded. The distribution overhead conductor is multi-grounded at many locations. Like it's not grounded only at substation. It is grounded about every kilometer of 800 meters apart, like every third or fourth pole. It is grounded. That's a 4th wire. And the loads, your house loads, single phase loads, are connected between phase and neutral through pole top transformer, which is phase to ground transformer. This is how the electricity came here. Finally, to the distribution system. So the focus of the discussion today is distribution system. Basically, look at the characteristic of a distribution system. In a traditional system, it was a unidirectional flow. The electricity traveled from source to the distribution system. There was a single uniform power flow. There was no power flow back from the distribution system to the network. So it was a single terminal distribution system in a conventional or traditional hierarchical nature of network. That's how we built electric system over 100 years. since the industrialization of electricity 100 years ago, electric grids around the world are built around it. Generation stepped up to transmission, sub-transmission level. Then electricity went to the low voltage customer, which is your and my home, through a distribution system. And distribution system was single terminal, unidirectional power flow from utility to the homes, to the consumers. Now, what is a distributed generation? There could be run of the river. Now, distributed generation is not a centralized generation. Your generation is distributed and not big generation, big generating station, 100 megawatt, 200 megawatt, 1000 megawatt. Now, in India, we are seeing even 6000 megawatt generating station facilities. You can have small generation facility like run of the river, or you could have a windmill, you could have a solar mill. Now, all these small plants, which are not even 5 megawatts, some of them in my utility will limit distribute, we limit about 15 megawatt, but I'm talking a small plant, like a 15 megawatt or lower. Or let's take it a plant 200 megawatt or a solar panel on top of your house. It cannot be connected to a transmission system, to a high voltage system, because the cost of converting electricity at which it generates the electricity and putting at a high voltage is so expensive that the distributed generation connection at transmission level, or at least extra transmission level, using a traditional method is not viable, it's not practical. It is going to kill the distribution generation. So we need to find, basically, a distribution generation can only be practically be connected to a low voltage grid, that is a distribution system, or maybe a sub-transmission system, not to a 500 kV system, extra high voltage transmission system. That's where our traditional centralized generation was connected. And again, when we are connecting them, what kind of issues we are going to introduce. So first, for the economics of distribution generation, we can only connect to the low voltage grid. But this low voltage grid, which is designed for a unidirectional power flow, it will not be safe if we just connect them and do nothing. So what do? We'll talk about that. But also, why are we bringing a generation next to the here? What are the benefits? Why do we want to do that? So we'll talk about that too. So module 1 is from a centralized to distributed generation, introducing microgrid opportunities, but creating new protection challenges. So we have a distributed generation connected to a distribution system, and what kind of things it's going to do. First, we will talk is what kind of problems are introduced by connecting a generation to a distribution system which is designed for a unidirectional power flow. And we will talk about it assuming this source is going to be connected only when it is running in parallel with the utility system. That means the small V source running in parallel, what kind of a problems it can create. Then we'll go to the next step. If it is running separated from the system, it is allowed to be formed a microgrid, what kind of problems will go. And very important thing in this is a grounding. We'll talk about grounding. So this is a traditional distribution system, very similar to what I showed before. High voltage or sub-transmission system, transformer, step down, then you have a 25 kV or 12 kV system, long overhead feeder may be going, single phase transformer, this may be a single phase pole mounted transformer, protected by fuse. Now you will have a protection here right in the substation. You'll have a substation protection, which is as an overcurrent relay, inverse instantaneous, and inverse time overcurrent relay connected to a CD and will trip this circuit breaker. This all is in the substation. Very important thing I want you to observe, although I will not talk in detail about it, this is a topic of transmission microgrid. I will not going to touch it, but I want you to see this topic very importantly. The transformer connection typically A typical distribution transformer connection is delta on high side on a transmission side, Y solid grounded on a distribution side. Why? Because this transformer provides effective grounding. The distribution systems are effectively grounded, at least in North America and most part of India too. So effective grounded system requires transformer to be delta on high side and Y solid grounded on low voltage side. Now this is a distribution feeder. I said distribution station protection, inverse time protection connected to a CT, and this protection will trip the circuit breaker if there's a fault on this feeder. Now this distribution feeder can have an overhead sectionalizer, which is a overhead sectionalizer is a device which is a circuit breaker and relay protection embedded into one, and typically it has its own power supply. That means it has a battery built in it. So it is the only drawback of this device is if there's a power is out for a very long period of time, battery discharges, you may lose this protection. So you cannot, this device will not work very well if there's extended outage. Otherwise, it is as good as a station protection. Station protection has a local battery and supplied by local backup power, so that if there's extended outage here, battery could last much longer. And there's alarms and all those things. This device is installed in field. There may not be good alarming system and maybe time to attend to them if there's a battery failure. But otherwise, for the purpose of this discussion, for the purpose of this presentation, we will consider field recloser to be almost same as feeder protection in that station. Now let's say we connected a run-of-the-river plant to this distribution feeder. So the run-of-the-river plant is here. Again, it will be connected to a transformer. The power may be generated at 400 volt, lifted up to 25 kV feeder voltage. Again, lifted to a transformer. We'll talk a lot about this transformer in the grounding part. It is delta on unit transformer, delta on the generator side, Y on the connection side or system side. I've shown Y solid grounded. I'll talk a little bit more about it. Now, so let's say this is a distributed generator connected here, and there's a recloser or something here. We'll not worry about that right now. And this is what we call is a point of interconnection. This is a point of interconnection where this generator could be owned by third party, private party connected to the utility system. Here, this is our POI. Now, if you have a fault here, now the current will come. So initially this resource is supplying a power to the local load here, maybe supplying some power here, may or may not be. But now once you have a short circuit here, the current will flow to the lowest resistance path, and current will flow from here, as well as short circuit current will come from here. Now, this recloser will see the current by this generator as well as utility system. So it is going to see more current than before. Good. So this protection sees a higher short circuit level, and so the protection will operate faster. We want this protection to be operate faster than that. That's the inverse time protection coordination. In the inverse time protection coordination, you want this protection to operate faster than this. So this distributed resource is helping this protection to operate faster. We are happy about it. Now, when I'm saying the short circuit current level is increased, first you have to check this circuit breaker or this recloser can withstand this increased short circuit level. If not, you have to replace it and put with a higher rating circuit breaker. So first point is, now short circuit current here is increased. You have to make sure this recloser or this circuit breaker has capability to handle increased short circuit level. If not, you need to replace it. So that's the first change you have to make, or not make if it is within that capability. Now, on the protection basis, it is good, but recloser, the circuit breaker basis, you have to make sure that it has an interrupting capability. Now, next point. What happens here? Now, some of you will be surprised actually. This was a surprise for me until I started to work. Once you connect a distributed resource here, the short circuit current for a fault here, you will find if you do symmetrical current analysis or symmetrical component analysis, or you do a simple short circuit analysis for a three-phase fault, even you do for a three-phase fault, you will find the current here is lower when this breaker is open. That means when this resource is not there for same fault. Exactly this fault, when this breaker is not there, this current will be higher, and after this resource is connected, when this distributed resource is connected, the current here will reduce. The reason current is reduced because now short circuit current got distributed in two parts. For example, very simple. Look, you have a one generator and it's supplying a short circuit current of 1000 ampere. Okay, you get another generator which the fault current is still 1000 ampere, like your path impedance is still same. Your current is going to get split into two parts. Basically, even when your short circuit current is increasing here in this case because of two sources, because the effective source impedance is reduced, you're having a higher short circuit current, but individually the current is dropped depending on the source impedance of the two sources. Obviously, the source impedance of a distributed generator is going to be lower, typically in most cases, not in every cases, in most cases is going to be lower than the short circuit impedance of this utility source. But still it is effectively it reduces the short circuit current from here. What it means that this protection sees a less current will operate slower. Good. We are even happy that this protection operates faster, this protection operates slightly slower. Our protection margin is improved, our coordination is becoming better. Why should we worry? We should worry in one case. Because this protection is seeing a less current, what if this protection fails? The inverse time protection is providing a backup. This protection is providing a backup to this protection. If this fails, this has to operate. Now the fault current reduces. If it reduces to a point, and that happens, if this source is strong and this utility source is weak, that happens in my system. The example I'll give later, I'll show you. If this source is weak and this source is strong, you will see much lower current here, and to a point that you may not even able to provide a reliable backup protection. That means if this protection fails, this is not seen, now you've got a problem. That's not acceptable. You need to make sure either you need to desensitize this protection or you need to do something else. You need to put another recloser in between here, which will provide a backup to this. So that if you provide a recloser here, now you have no risk. Now that recloser is seeing the total current, it is no desensitization. So that's the decision you have to make. Do you need to put another recloser, another protection device here, which will provide a backup to this, and this will provide then backup to this. So those are the decisions you need to make. What I'm making a point, there's a protection desensitization here. And you have to look and accommodate for, you have to do protection changes. You have to do system changes. You need to install more protection reinforcement to accommodate this if that's the case. Typically, the good news is this desensitization is not there for phase faults. This desensitization is mostly there for the ground faults. Why for the ground faults? Because ground faults have a resistance in them. Phase faults do not have resistance. So typically, at least in my experience, except for one time out of hundreds of cases, I found there was a phase desensitization here. Otherwise, 99.9999% cases, there was no phase fault concern. There was always a ground fault concern. And I'm going to tell you how to resolve the ground fault concern later on, just in a few minutes. That's point number one. Point number two, if the fault is here, reverse. Now you have a bidirectional power flow. This protection was originally designed to operate in this direction. It's a non-directional protection. Good, if the fault happens to be here and this fault current is not high enough, if this resource is so weak that the fault is not high enough, then you have a problem here. You need to assess it. You may have to put a directional protection, which is very sensitive directional protection looking this way, depending on this distribution resource, so that it can detect the faults in reverse direction. And if there's a fault in transmission system, even a bigger problem. Why it is a bigger problem? It is an ungrounded transmission system, because now you have a ground fault here. There's no current withdrawal. You need to look for another alternative. You need to put a line transmission protection. You need to use what we call ungrounded protection system. That's another problem you need to solve. So what I'm telling you, there are many protection challenges to overcome. Obviously, given this 1 hour, I cannot discuss all those challenges. I cannot give the solutions of all those challenges. I'm just introducing those challenges to you and encourage you to read one of my reference paper given. It describes how to overcome these challenges. In this 1 hour, it's not practical for me to go through the solution. Now, so these are the protection challenges of connecting distributed resource. Now, what are the benefits? One of the big benefits we are talking, microgrid. Now, microgrid is basically allowing this resource to operate with this feeder, with this breaker open. When this breaker is closed, the resource is operating in a grid connected mode, and with this breaker is open, we are allowing microgrid to operate. We are allowing this resource to operate and serve this load customer while this grid supply is gone for some reason. So we are, by using a local generation, we are improving the reliability of the supply, not to mention reducing the losses, better voltage regulation, all those benefits. But one of the big benefits, you lose a grid electricity, you have a local source to supply your loads. So you have a better grid improvement reliability. But we have a better grid reliability, but with this breaker open, now the short circuit current seen by this protection is significantly low. The protection 51R has to operate correctly when it is closed, when it is operating in parallel, and also has to work correctly when the grid is isolated. So it has to work in both modes. So I'm going to present solution to microgrid, some of the microgrid problems later on my examples. I will not be able to discuss line protection problems, solutions, and so I will, as I said in the scope of my presentation, the transmission issues will not be discussed. I'll discuss the remaining issues as we go along, okay, as I talk about an example. So one thing, how do we overcome protection desensitization for ground faults? That is the biggest challenge. That is the biggest challenge. How do we overcome? So I'm going to talk a little bit about it, grounding. So what I had told you earlier, there's a transmission line and supplies to 25 kV distribution system, connects to delta star transformer, as I shown in the last line. Transmission line connecting to this distribution station. This is a physical representation. This is a one-line representation of the same feeder one-line representation. And that transformer, this transformer, single phase transformer, really looks like this. There's a three-phase feeder, 3 lines, A, B, C, 25 kV line, and there's a neutral here. There's a neutral here, 4th wire, and this is a single phase transformer connected between the phase and a neutral here. You can see that. And it supplies a single phase load. Actually, the neutral is in the center, and it's a 120 transformer plus 120, two phase. It's a 2-phase, single phase one. 120 phase here, 120 phase here, and the center is a neutral. So it's going to 2 houses, A house and B house, like that. So this is a single phase transformer with a neutral, center neutral, and 120 volt here to 120 volt here, and look at this is connected to single phase. So single phase transformer, base to ground voltage here, that's what it is, pole mounted transformer. Now you are connecting this distributed energy resource, which I said unit, this side is delta, this side is Y. I said dotted Y grounded here. What grounding it should have? Let's talk about it. What grounding should be for this transformer? Now, we could leave this transformer to be ungrounded for a minute. If we leave it ungrounded, we could leave it ungrounded. Then if there's a short circuit, for example, here or anywhere in this feeder, as we saw earlier, we saw this example, the same short circuit. We're talking short circuit here. And this transformer, for a minute, I left it ungrounded. The same thing here. So we left ungrounded, a short circuit here. Now this ungrounded transformer, no ground fault current will come from here because ungrounded system. Only short circuit current come from here. Protection here, that 51 protection on the station which we are talking, this protection here. We're talking this protection here. The fault is here, we're talking this protection, but grounded, so no current is coming from here. No current is coming from here. This current is not coming. Only ground fault current is coming here. And this protection will operate and open the circuit breaker. That's what I'm talking. I want to make sure all of you are with me because this is a very important point. So the fault current coming here, ground fault current coming here, and this circuit breaker open. Now this circuit breaker open, no current is coming, no protection. This protection will never operate because no ground fault current coming. Now, this got subjected to, it's a line to ground fault. This source is still connected. We subjected to √3 higher voltage because of neutral shift. This is a ground fault here. There is no neutral. Neutral will shift to the faulted phase. Now the phases are subjected to line voltage. This transformer is now subjected to line voltage. It is √3 higher voltage. It will get severely saturated. High eddy current will flow and will damage this transformer. So if you unground, that's what is going to happen. You will need also a different type of protection, which we call zero sequence overvoltage protection. We also use in transmission line zero sequence overvoltage protection, but zero sequence overvoltage protection cannot be operated instantaneously because it does not coordinate. It has always have to be slow, time delay. It has to have 15 cycles of a time delay or even longer, and that time is too long for this transformer to subject it to overvoltage could get damaged. Or that even sometimes the time has to be longer than 15 cycles, depending on the clearing time here. It could be much, much longer, could be seconds, and could damage this transformer. So you would say, why not ground it? As I was talking, why not we do grounding? Obviously, we can do solid ground. Now we do solid ground. As I said, ground fault current will come from here, and ground fault current will come from here, and will lead to desensitization of this ground protection. And if this source is very strong and this transmission line happens to be very long, for a weak source here, this protection may not see this fault and may not clear until this opens. So that's a challenge. So that's the biggest challenge, or may not provide a backup for some other faults here. So if this fault current becomes so low that this protection will not operate, that's not acceptable. So that's a trade-off. You do solid grounding, and the reason I say there's a fault resistance here, the fault resistance happened to be here, and the current coming from here, even both of them may not be able to see. Neither of them may be able to see. So how do we overcome this challenge? There could be a middle way. There could be a middle way is basically instead of doing a solid, actually, I want to make one more point. Actually, you will be surprised. This is where you learn when you work in a utility. The desensitization is worse actually when this circuit breaker is open. That means when this generator is not operating. Why it is worse? Because this transformer acts as a source of zero sequence current. That the fault current comes here, and also it flows into this path, and it circulates through this delta. Actually, I'll show you a record. This is a record. This is a fault record when there's a line to ground fault current here, and you will see three-phase currents coming out of here, and you'll see what interesting three-phase current coming out of here. So I'm going to say voltages. I'm going to show three-phase voltages here, and three-phase current when no source is connected here, when this breaker is open. Look at the current. All three currents are in phase. A, B, C current are in phase because there's no positive sequence voltage source behind it. The delta transformer is circulating a zero sequence current and sucking up all the current from utility side and providing a zero sequence source. This is how it is. That's why this transformer has another name. There's a second name for this transformer. This transformer is also called a zero sequence source. It is not a positive sequence source. Positive sequence source is disconnected and it supplies a zero sequence source. So it's a ground fault. One of the phase voltage is low, other phase voltage is low. There's an explanation. I will defer that one. So the transformer is a zero sequence current source here. Look at the fault. Before the fault, there was very little current going. There's a very little current. It was a residual current. And as soon as fault happened, and there was a lot of current going here. Sorry, I apologize. Fault was here, and as soon as this breaker opened here, for some other reasons, there was an all zero sequence current. So what is the trade-off? How do you overcome this problem? Ungrounded poses a risk to single phase loads. Ungrounded transformer is a risk to the single phase transformer. The grounded transformer reduces the protection sensitivity. So where do we go? There could be middle path. Do a reactance grounding. If you do a reactance grounding and keep the reactance to the equal to the leakage impedance of this transformer. If this transformer has 8% leakage impedance, make this reactor to be 8% or 1.58%. What will do? It will limit the voltage rise or neutral shift so that the voltage rise is about 125%, which is within the limits of single phase transformer. Basically limit the voltage to less than 1.3 and also help with desensitization. So that's one compromise we make in our utility. That's one of the compromises available. Again, you need to assess, you need to study, rather than give you what you need for now. Now I'm going to switch 2 to 1 rule. 2 to 1 rule is on a premise. I'm going to say what is the basis of this. I'm going to describe what is the basis of this rule. This rule is based, and then I'll describe a concept called sustainable islands, and then I'll show you an example of sustainable feeder island. Again, the tutorial is limiting only for sustainable feeder island. I'll talk about it then. So, as I said, distribution system is not designed to have multiple generation sources or bidirectional power flow, similar to transmission system. So once you connected a resource to a transmission system, its characteristics become like a transmission system. But if you apply transmission system protection, which is very expensive, transmission system protection is very expensive. If you apply transmission system protection to the distribution system, you will kill the viability of the distribution resources. So that's not going to work. That's going to kill the distribution resource. But if you do nothing, as it's an unsafe condition, you cannot have a fault and not detect it. So what I'm making a point, applying a protection upgrade similar to transmission system are very expensive, but not doing anything is unsafe. So what do we do? That's where our 2:1 rule is coming. The rule is, how do you define? So basically the rule is, if the resource is big, resource is large, very large, you can put protection upgrades, expensive protection upgrades, because there's economic sense. You're going to have more electricity from that resource, you can spend some money in connecting it. If the resource is small, like your pole top, solar panel, which is a very small, and you put a transmission type protection upgrade, you are not going to even bother about it. So the point is, how do you define a big or small source? How do you define a source as a big or small? That is what it is. How do you say this source is big? 5 megawatt is big, 7 megawatt is big, or 200 kilowatt is big? How do you say what is big? If someone says 500 kilowatt is big, then someone says why not 1000 kilowatt is big? I think I'm having some disturbance on the thing. Is it everybody okay? Can you hear me? Nora, are you able to hear me?
Yes, sir, it's fine. It's fine. I guess there were some glitches from some other person.
Okay,
so I have muted them.
It happened to me one time. I did my 1 hour tutorial. At the end, I realized I was talking to myself. There was a connection problem.
No, sir, it's audible. Otherwise, I would have pinged you.
I was doing a last presentation in Australia, and after 1 hour, I realized I spoke to myself. Okay, what is 2:1 rule? So, Gaurav, if you don't, I think I should have given you my telephone number. Anyway, 2:1 rule. An island. It's a 2:1 rule. Permits is an island with a connected load twice. Connected load twice as much as of islanded generation is not a sustainable island. That's the premise of 2:1 rule. That means what it means. If you form a microgrid, for example, you form a microgrid where the load is twice as much as the generation, that microgrid is not going to be sustainable. That means protection and control of generator are going to kill it. So if there's a fault, you separate from a utility. And you separate so that the generation in the island is half the load in the island. The fault is going to be self-clear because the source is going to go on a path of suicide. The load will kill it. Basically, if you look at the Singh equations, this is just a simple simulation of the Singh equation where the generation is half, or basically generation is reduced to half of, or 1 month. Load is -1 per unit, and the damping is you use a damping of 1.5. If you do a simulation of the Singh equation, you'll see the frequency will automatically drop so fast within seconds that your source will not sustainable. I think you guys are. This was good to show to my colleagues who are questioning 2:1 rule, but you guys are all going to university and all. You know the Singh equation very well. When you work for 15, 20 years, people forget about basic things. They say, okay, what about 2:1? What about 3:1? So that required some convincing to colleagues 2:1 rule. And I'm going to come a little bit more about 2:1 is. 2:1 rule is basically first assures even with the load damping. Load damping is effect mean like you have an induction motor. If the frequency drops, the load of induction motor also drops. So that's called load damping. The point we are trying to make that if the load is twice and generation is half, or the load is twice the generation, you are guaranteed to kill the generation. That's all the point I'm trying to make. I was giving the same presentation at Delhi University. There was a student who argued, he was constantly hung up on this thing. He says, and he was rightly so. He said, even if the load is 1.1 of generation, it is going to go, if the generation is going to die, it all depends, The frequency will go down, may settle at 58, 57. It all depends what kind of controls are there. So I'm not that's the way the protection engineer. I'm just saying 2:1 rule. So that's a rule we have used. We have published it, and it's been now industry acceptable rule. 2:1 rule. And again, 2:1 rule is not about the load damping and this thing. 2:1 rule is a margin too. Is a margin. What if your load today is twice, tomorrow is 1.8. If you go by 1.1, let's say your generation is 1 and load is 1.1. If tomorrow, for some reason and some time of a day, your load is lower than 1.1, then you can form a sustainable island. The point we're trying to make is unsustainable island. To guarantee that your island will not sustain, that's a 2:1 rule is. So what it means, you can form a microgrid, which we call it a feeder island, if this breaker opens. And you can form a bus island if this breaker opens. You can form a transmission island if this breaker opens. And basically, you can form 3 types of microgrid: at feeder level, at bus level, or transmission level. So if you are able, if your feeder load, if this feeder load is minimum, like if your minimum load, you take a historical data. But so what we do, we take our historical 25 years of data, and minimum load in 25 years happen to be twice the generation. Then we say we don't need to worry about any protection upgrades there. All we need to do is microgrid protection now. We don't need to worry about if once this open, this will not sustain as a whole feeder. This microgrid is not viable. Let's not even worry about it. Microgrid is not viable here. Let's not worry about it. Unless generation is increased, we can connect this distributed resource only in the connected mode. This distributed resource can only survive in a connected mode. It cannot survive in microgrid, so let's not worry about it. So we don't do any protection upgrades here. Likewise, if this can form a bus island, we don't do any bus island protection upgrade on a station like bus transmission station. What this 2:1 rule does is basically allows you to optimize your protection upgrade based on a feeder and load ratio or microgrid ratio. If your feeder load is approaching the generation, then you need to do protection upgrades at the feeder level. If it's approaching the station bus level, you need to protection upgrade here. If it's approaching transmission level, you need to add line protection. So that's how you optimize your protection. So an example, if this is sustainable microgrid, if this feeder protection is sustainable, if this generation is enough to support this load, can form a microgrid, then we need to make a protection upgrade here. Now, what is our protection upgrade in BC hydro? If it is a sustainable island, then we want this protection here to be modern microprocessor based protection, which has the ability to disturbance record so that we know what's happening in the system, and it also provides us multiple setting groups so that we can use one group when it is operated in a connected manner, and we can use a different group when it is operated in a microgrid manner. So those are the compromise, those are the things we do. Basically, if it is going to sustain as a microgrid, we will put a modern feeder protection here and will allow it to operate as in a microgrid manner or in a connected manner. So basically, when we put a modern protection here, so this is a modern protection here, it's like a microprocessor based relay, which has a 3-phase protection, ground protection, and plus we put another additional, typically we don't have a potential transformer here on a distribution feeder because it's a unidirectional flow of a power. We don't need a PT here in a normal distribution feeder, but once we put a source here, and if this source can form a microgrid, then we need a PT here to make sure to allow a synchronizing or sync check closing here. Because if there's a source here, you can't close this breaker without having these two protection to the system to be synchronized. So we have to add a PT here for a sustainable island. We have to put a modern protection here. So these are kind of optimization we do based on 2:1 rule. If the feeder island is sustainable, we need to add this thing. Okay, I'm going to jump to module 4 now and then come back to the module 3. Okay. The reason I wanted to jump to module 4A, I thought if I run out of time, I wanted to show you something very interesting, which I think probably some of you know, but I wanted to share with you their real experience, even if someone may know about it. I'm going to talk about a microgrid with the inverter source. That's what is, I think some of you may find much more interesting than the other example, which has microgrid with conventional sources. So what it is, this microgrid is formed by battery storage, and so what I'm going to talk is the battery storage system which is a basis of this microgrid. And there's a grid follower versus grid forming mode in which this battery storage, the control system of battery operates on. So battery as an inverter operates either in a grid follower mode or grid forming mode. Then I'm going to share with you the last part. I'm not sure if all of you have seen unique fault characteristics of an inverter-based resource. That's what I'll share with you. What this is a distribution feeder in our company. There's a substation here, a just 25 kV substation here, and it is supplying to a very remote community, which is the name is field, and there's a golden station here, and this is about 60 kilometer long 25 kV feeder. And you can see this is a geographical terrain, all mountainous. I live in a very beautiful place called British Columbia. A lot of mountains and rivers, beautiful place. But it's a very rough terrain, and this is a rough terrain. So this feeder travels through a very rough terrain, and also it runs next to a railway line. So if there's an outage on this feeder, there's a mudslide or somehow a snowstorm, if this feeder is lost, it takes long time to repair it. It's not a way is to dispatch crew so far away on this rough trail. If there's a snowstorm, the road is not very good for the crew to go there. And then there's a railway track. You need to coordinate when the crew is working on a overhead feeder. You want to make sure there's no train coming by and causing a hazard. So there's a lot of coordination. So the community suffered many outages because of this train for many years. For many years, they lived with it. That's the best we could do. There was no economic. It was very expensive to put another alternative supply through a different path. Because of terrain, it was not economically possible to serve this community, which has only 1 megawatt load. For a 1 megawatt load, it was not practical to put another second supply. Although all loads are important, but you got to draw some economic consideration. So that's one thing. Second thing was happening is, so we did really nothing. We had to live with it. But one thing, an opportunity came. Opportunity came for a different reason. The substation transformer. There were other loads. This station is supplying a load here. It's a very good resort area. There is some industry here. So the distribution station the transformer had reached its peak. Like on a very cold day, the transformer loading was exceeding or was approaching its maximum capacity. So basically, there was a need to replace the transformer to serve the peak load. So that was replacing a transformer is expensive. So an opportunity came. Opportunity came here is what we decided. We are going to put a 1 megawatt battery. Sorry, not 1 megawatt. 1.25 MVA battery here, right next to this community. It did two things, two benefits. It shared the peak. Basically, when there's a peak load, and the transformer was just approaching its peak load. So we got 1 megawatt peak of supply from a battery for the peak hour. So battery shaved peak by 1 megawatt, 1 MVA. And then it did a reliability improvement. When we lost the feeder, and the battery is, I'm going to show you in a minute a battery. So battery could supply in a microgrid our load. Here it is. This is a one-line diagram of the feeder, that 60 kV, I told you about 55 kilometer long, 60 kilometer long feeder, and this is a battery. These are two batteries, and two batteries together, together I think one megawatt, or inverter is 1.25 MVA. The battery storage is 6.5 megawatt hour, which can supply for an extended period of time for this community power. Can supply at least 8 to 10 hour power to this community by the time the crew can come and restore the power in most cases. So the minimum load on the feeder is 2 MVA. There's some load here, some load here. There's some load here, some load here, and this load is about 500 kVA, but total feeder load was minimum load is 2 MVA. Battery is 1.25. So that means 2:1 rule is based on 2:1 rule. It's a sustainable island. Sustainable island from a point of protection update. For example, if we take a margin here, if some of this load is not there for some reason, so just being conservative here. So based on this ratio, this does not satisfy 2:1 ratio. We upgraded this feeder protection. We put a PD here, we put a new protection here, and there are feeder reclosers here. And this is our inverter. This is our inverter connected to this feeder to a delta star transformer. This side is delta, this Y grounded. Now Y grounded, solid grounded, because this is 55 kilometer long here, and this source is relatively strong. So for a fault current here, there was a desensitization here was so small that there was no need to put an impedance grounding here. The fault current from here was not, this source was not strong relative to this strong source for a fault here. So there was no need to worry about the ground desensitization or phase desensitization. So we put a new PD here, new protection here, and this is a device called intelligent disruptor. What it does, whenever there's a short circuit, whenever there's a fault here on this rough terrain part of the feeder, this is a rough terrain fault. Whenever there's a fault here, if the fault is here, you cannot do anything. If fault is here, right in this small part, this 3 kilometer part, which is a rear. If there's a rear fault here, this intelligent disruptor sees a forward fault. I want you to pay attention to it. It sees a forward fault and it makes no action. It does not. So this intelligent disruptor gives a signal to this inverter that I want to go in microgrid mode. When it sees a fault here, sees a forward fault, it does not give a signal. He says the fault is in front of me, the fault is here. Even if you form a microgrid, you're not going to help this community. Don't even form a microgrid. But if the fault is here, it's a reverse fault. But unfortunately, I'm going to show you later on, this battery source, because of this battery source, this cannot see a reverse fault. I'm going to show you that later. And first, before that, I want to talk. I've missed something very important. When this source is connected, when all these breakers, red mean these reclosers are closed. All these breakers are closed. All these breakers are closed. When all these are closed, this battery source is operating in a grid connected mode. That means the control system of this is operating in a grid following mode. Grid following mode means this is a current source basically two things: doing charging a battery or helping to shave the peak load. Only supplies balanced 3-phase current. Very important point. In grid following mode, it supplies only a balanced 3-phase current. That's how this inverter is designed. This inverter does not supply unbalanced current in the grid mode. Grid following mode, all the unbalanced current come from feeder. When this is open and this battery is operating like a microgrid here, supplying this load, the control system is switched to grid forming mode. That means this control system of this inverter will be called grid forming mode. It will be controlling the frequency and voltage as well as supplying the balanced unbalanced current. That means it will supply the single phase load. Single phase load, the unbalanced load. It is be able to supply unbalanced load too. Just give you an example. This slide is borrowed. Actually, I said it's borrowed from this tutorial. I repeated the tutorial. is showing an inverter source. Y-axis showing the voltages, this side of y-axis showing voltages, this side of y-axis showing the current. A three-phase fault is applied. So look at the voltages are nicely balanced. These are the current before the fault. And three-phase fault is applied. Initially there is some transient and the voltage collapse. Three-phase voltage collapse. And three-phase current is almost, number one, the current is almost equal to the pre-fault current. Number one point, that the battery source or inverter source short circuit current is unlike a regular conventional source. Conventional source, the current goes up. Here the current is almost same order, at least in the same order for an inverter source. Now look at this. When it's operating in a grid follower mode, let's say you apply a line to ground fault. This is a line to ground fault. These are experimental results of the same thing. So this was a balanced fault. Now let's look at unbalanced fault. It's an unbalanced fault in a grid following mode. Grid following mode when it is supplying balanced load. It's not supplying the balanced current. The grid following mode, it acts as a current source, only supplies the balanced current. For a line to ground fault, it's still supplying the positive sequence current, even when the voltage is unbalanced. The inverter control takes in, still supplies the balanced current, unlike a conventional source. But when it's operating in a grid inverter mode, it supplies positive, negative, and zero sequence current like a conventional generator. Not so much, I'm going to show. Not exactly like a conventional generator, I'll show you on one more fault record. I'm going to show you a little bit more. First, so there's how does it get transition happen? If there's a fault here, this obviously protection, the recloser, this recloser will open because these are closest to the fault. It sees a forward fault current. It sees a forward fault current. It does nothing. It does nothing. Because forward fault current grid, there's no point forming a microgrid if this is a permanent fault. It's only if it's a temporary fault it can do something. So basically, if the forward fault happens, it's not going to do anything. If it's a temporary fault, recloser will reclose, the supply will restore. Now, if you have a fault here, if this same fault happens to be here, it will not see a forward fault. Basically, a permanent fault happens here. First will happen, a permanent fault happen here. This will see a fault current coming from here, but it does not recognize as a reverse fault. I'm going to tell you why later on. It has to rely, if he sees it is not a forward fault, that means it's a reverse fault. The logic is, if I don't see a forward fault, it's a reverse fault. I'm going to tell you why it is not see a reverse fault. That has to do with the battery. I'm going to come back to that later. But let's take it, there's a fault here. It's a permanent fault here. This recloser will open and this raptor will open and the fault is isolated. The recloser will reclose. If the power is restored, and then someone will close this thing and the power will go back. But if the power is, if this is a permanent fault, reclose attempt will fail. So once the reclose attempt is failed, then this interrupter, after 30 seconds actually stayed in this, when it sees, after reclose attempt failed, when it sees there's no forward fault, it says, I see no forward fault. I did not see a forward fault, and I see the voltage is gone for 30 seconds. That means the reclose attempt has failed. Then it signals this guy go into grid forming mode and form a microgrid and supply to the load. So basically, so if the fault, for a fault here, it cannot do anything, but for a fault here, it gives a signal to this, and it can form a microgrid in a grid following mode. Now, I wanted to come back to you and tell you why it cannot see a reverse fault. We had actually a situation. We had a permanent fault here. So the fault happened, this recloser opened and this intelligent interrupter opened, and it was open for some time. And finally, operator tried closing this one, again it faulted. It did not, because it was a forward fault, and intelligent interrupter did not go in a microgrid mode. It said, no, I see a forward fault. Then I think system shut down. That an hour later, operator thought, let me take a chance. Maybe this was some small tree came and tree touched the conductor, the tree is clear, the wind has gone, the tree is gone. Let me make an attempt. The operator made a manual attempt to form a microgrid. He did a black start. He tried to do a black start. Operator tried to do a black start. It was a permanent fault, and we captured the record by this relay. So we captured the fault record for a relay by this relay. I'm going to show you. Actually, this was A to C ground fault. Yes, I think you cannot see. I'm going to move this thing. This was A to C ground fault, and see the waveform. You see, it's A to C ground fault happens to be very close to the relay. The voltage A to C collapsed, and this is a B phase voltage. Actually, B phase voltage also depressed quite a bit due to high current. And look, the current in the other two phases, this current was limited by inverter to the I think 2 per unit. In this specific inverter, this inverter limits the current to 2 per unit. But anyway, it limited the current. It did not go too high, but limited current to 2 per unit. And this is what's showing you positive sequence current. And this is a zero sequence current. Red is a zero sequence current. And this is a negative sequence current. We see a lot of zero sequence current because remember I showed you a transformer, delta transformer. This is a Y, this is a delta here. Delta is a zero sequence filter. And if there's a ground fault here, you see, delta transformer is a zero sequence current source. If there's a ground fault here, it supplies a lot of zero sequence current. In spite of that, it is in a grid follower mode. It supplies very small amount of negative sequence current. And this negative sequence current is not inductive. This is a very resistive negative sequence current. What the point I'm trying to make, in a directional element, a negative sequence directional element relies on a phase angle, inductive phase angle relationship, where the current, negative sequence current, leads the negative sequence voltage by 90 degrees. Here it leads by 180 degrees. So this device cannot make a directionality decision for unbalanced faults, unbalanced phase faults, the faults which are not involving ground. It can make a decision for ground faults because the ground faults, ground current is coming from a delta. Look at this, ground current is coming from a delta and it has a 90-degree angle. For ground faults, it makes a good decision. For a phase fault, it has to rely on negative sequence. It cannot make good decision because the negative sequence characteristic is not like a conventional source. It depends on grid inverter control system. Therefore, it can only detect a ground fault correctly, direction of a ground fault, not a phase fault. So negative sequence it cannot detect, and zero sequence, the zero sequence direction element can work because of the transformer. So these are the conclusion of my presentation. Now, before I go, Gaurav, do you have a time to continue to talk about other things, or should I stop there?
So we can continue if you want.
So I go on module 3. Okay, I'll talk about module 3. In module 3 is a microgrid example. Now this example with conventional source, and this is a very complicated example. And also in this case, it was not built, the system was not built for a microgrid operation. It was built to connect distributed energy resources for peak shaving, for local supply, for energy purpose. The original intent of connecting distributed energy resources in this part of the system was not a microgrid. We subsequently made incremental changes to allow it to operate a microgrid, and that's what I'll talk. So because it was not originally planned for an operation of a microgrid. The microgrid operation is a planned operation, means in the previous case, when the fault happened, the switch from a grid to microgrid happened automatically. In this case, switch to microgrid from a connected to microgrid or microgrid back required certain manual operations because we did not put enough communication infrastructure to allow it to operate to do automatic transfer. So I'll talk about some of them. So what it is, I'll talk three things: the system, then what kind of things we did to make it work as a microgrid, and then in spite of doing all good things, we still had in a microgrid operation, we did have at least in two occasions unplanned trips. I'll share with you those. The system is, again, like before, it's a transmission system. It is an integrated BC hydro system and supplying through a very long 320-kilometer long 130 kV transmission line to a small distribution station. It's a 25 kV distribution station, delta high side, Y grounded, and has three overhead feeders. And each of these feeders is very long feeder. And it was not, as I said, over a time, not for the reason of microgrid, not for the reason of reliability of supply to this. For other reasons, we had a lot of this is a very beautiful place with lots of rivers, and private investors came in the deregulation, came with us, and they put in, and we got 7 run-of-the-river plants connected to this small location. 7 run-of-the-river connected, 7 privately owned. We are calling them IPPs, got connected to this small station for a period of time. Now we got 7 connected, but in spite of we had so much local generation, so much local generation, whenever there was a maintenance work on this path or there was an extended outage, we relied on a local diesel generator to supply them the power. You can see how bad it is. We were using a polluting generation, expensive generation, to supply these local loads. In spite of that, we had a local power. We thought that makes no sense. That's not very good. So it was not even a company project. Few of us took upon us. Our operating staff worked with some of us in engineering. Just operating staff took a lot of pride in the green energy. We worked together and made a microgrid work. But so we'll talk about it, some of the things. Number 1, I wanted to make a point here is this is same as before, like similar diagram as before. Transmission station, long transmission line, distribution load, station, and the feeders. 3 feeders here. I'm just talking 1 feeder. So one of the IPP is 10 MVA, 2 into 5, 2 into 2, 2 generators of 5 MVA. The entire station load is less than 10 MVA. But I'm trying to make a point. The station load is this one IPP, this one generator can supply entire station load. So that means it can form a microgrid with feeder. It can form a microgrid with all 3 feeders. It can form a microgrid even with some of the transmission loads. So this IPP being 10 MVA required lots of protection upgrades here. We had to put a modern microprocessor-based protection here. We had to put a line protection here because the power was by flow, and we had to do some little bit of work in the station bus protection. Large generator, large upgrades. We put new feeder protection, we made modification to bus protection, we put a new line protection. These are the details of the station feeder. There are 2 feeders here. 3 feeder, 51, 52, 53. This is the longest feeder, 52, which has an IPP1, the largest 10 MVA generator here. This is the second largest and third largest. Rest are very small. There are 7 IPP. Now we decided, some of us, that we have all the infrastructure and we have ability to supply this load. Why not operate as a microgrid? we said we will operate these three generators to supply the load depending on the water in the river. All three of them can supply the river this station load. So we selected, basically, we selected this IPP1, the largest one, as a master generator. It has a black start capability because if you have an unplanned outage, as I said, it is not a planned microgrid. If you have a fault here, everything trips. We need to start. Even if we need to start, we need a black start capability. So this one has a black start capability. That means if station goes black, we can pick up the load by black start and form a microgrid by black start. Okay? This can support the entire station load. Therefore, we selected a microgrid. And plus, it being largest one and also had a relationship with these two people, it had the ability to control these two plants too. So this is a master station for three reasons. Large, and this has a partnership with these two plants. So it has the ability, there's a one common control center among three, but our own control center here has no ability to control all those three. If we had ability to control all these three generators, then we could have done a plant transition. We don't have an infrastructure or SCADA system to operate and control these three IPP by our control desk. That is a BC hydro control desk. So other two generators are small, 3.7 MVA. Grounding, very important because we are going to operate grounding. This IPP is going to serve as a microgrid, and we decided, and this one was a solid grounded, delta Y solid grounded. Now you should ask me a question. This is the largest generator, weak system. If we do a solid grounding here, we are going to have a desensitization of ground fault. Yes, we are going to have it. But how we overcome that thing? We put a very sensitive ground protection here. Anytime there's a fault here, when it is connected, we have put a very sensitive ground protection when it is in a grid connected mode. When it is a grid connected mode, if the fault happens to be here anywhere, this protection will operate immediately, thereby restoring the sensitivity of it. So we set highly sensitive ground protection on this for the grid connected mode. These two generators are not expected to serve in an islanded mode, and they are not going to survive as an island, and they are impedance grounded using the method which I told you. But they are impedance grounded. They could serve if we wanted it, but we have decided they are not going to serve they were not going to serve in a microgrid as a standalone. 2 and 7 will be connected in a microgrid mode only if one is connected, which will provide a very good effective grounding. Effective grounding will come from 1, 2 and 7 are impedance grounding, and as long as one is there, we will have a very good grounding. Very important thing. The reactor, we saw inverter mode. We talk of a grid following and grid forming. These are the new terms, sexy terms used by the electronics engineer. What did we do in the old days? We didn't have a grid forming grid following mode. Actually, we had a different name. The IPP1 in a microgrid mode. In the microgrid mode, operate is called isosynchronous or zero droop mode. That means it is like an infinite inertia machine. The frequency and the voltage control of is fixed when it is operating in a microgrid mode. And the regulation, the load going up and down is helped by the droop from machine 2 and 7. So 1 is supplying a fixed base load, controlling the frequency and voltage like a utility system. 2 and 7 are providing a droop and voltage control depending on regulation. Now, the challenge was the fault levels are very low. The fault levels are very low because this is a very long, 52 kilometer long feeder. Fault levels are very low in a microgrid mode and connected mode. So we have used 2 sets of protection, normal and microgrid island. Look at the phase protection Our standard phase protection pickup is 400 ampere. In a microgrid mode, we have only 75 ampere. And this switch happens through a SCADA system. We have a SCADA control in our control room, and we can switch it remotely. This thing. Likewise, grounding. In a microgrid mode, in a normal mode, we use 240 ampere. These are our standard settings. In a microgrid mode, we have used a much sensitive setting. So we can toggle between the two groups of settings. This is the advantage of microprocessor-based relay. You can change setting through a simple control command. A control command coming from a SCADA changes a group from a less sensitive to more sensitive setting. Then very important, our feeder protection. Our feeder protection we do not use when we are connected, when we are operating through a utility source. When we are connected to a utility source, there is no frequency protection on our feeder protection. But we have a very sensitive frequency protection on that, because we have we want a planned microgrid. We do not want a microgrid when the fault happens here and it forms a microgrid, because when it is operating in a connected mode, all of them are operating in a group mode. They will not be able to control the frequency properly. We need to transition IPP1 into isosynchronous mode in a microgrid mode in order to maintain frequency and voltage within our CSA requirements. Therefore, we do not allow what we call unplanned microgrid. That means if there's a fault happen here, we want them also to trip. And to do that, what we call our anti-islanding protection. Our anti-islanding protection is on the generators. The generators in a grid connected mode, their frequency protection is very tight. Even a small deviation causes them trip. But in an island mode, their frequency protection switches to a very desensitive protection. So in a grid connected mode, they are very sensitive frequency protection, which trips as soon as there's a fault happen in system. They also trip. But in an island mode, they don't trip for a small variation in frequency. Also, I was trying to say, our feeders in a grid connected mode have no frequency protection because they are getting supplied by the system. But when they are operating in a grid connected mode, we at least two feeders, this feeder 51 and 53, have an under frequency load shedding. I'll explain to you why. The reason, and also I want to tell you, in an islanded mode, 53 Hz is an instantaneous trip. If the frequency drops for any reason to 53 Hz, the microgrid collapses. We trip we kill the microgrid. At that point, we think the frequency has gone too low. There's no way of microgrid will survive. We kill it. What I wanted, I'm just going to show an incident, and then I'll show you why we have a load shedding on feeders when they are operating in microgrid. I'll show you an incident. So, in spite of all good planning, in spite of all those things go wrong. We had a work going on. We had some work going on a transmission system. So we were operating this station in a microgrid. Actually, IPP, all three IPPs, I can't remember these three IPPs were connected or not. I can't. But this was operating in a microgrid mode. I can't remember which one, or all three. So this was operating in a microgrid. These breakers are open. These breakers are open. And now all the work got over. We were operating in microgrid for days. Now all the repair work was finished. Now we were trying to we are going to restore. We are just going to close the system back without causing a customer outage. We're just going to now synchronize these things back to the system across. Like we are going to synchronize them. We're going to close all this breaker to a sync check and synchronization. That was the plan. So what happened? this transformer does not have breaker. They have a disconnect switches. So what happened? There was some SCADA mistake. There are these capacitors here, and there was a mistake that indication of this capacitors was incorrectly sent to the control room. They were showing these breakers are open. Actually, they were closed. So operator had a indication these breakers are closed. So he started. So actually, there was a current flowing. There was a current flowing like this. See, these breakers are open. These breakers are open, and there was a current flowing here. And no one was checking the current. They just saw the status of this is closed and this is closed. But there was no recording of current flowing here was in the control room. Control room did not have this recording of current flowing here. Only they had indication that these two breakers are closed. So in a process of switching sequence for something operator wanted to do, wanted to check this transformer before closing this thing. He wanted to do some check. So what operator did, he opened this disconnect to isolate this transformer to do some checking. He thought this disconnect can only open when there is no current. If there's a current here, this disconnect cannot open. So this was a bad indication. So the operator opened this disconnect. Because there was a current flowing, this disconnect was not meant to open or interrupt the current. And therefore, when it was trying to interrupt a current, it flashed over, caused a real fault. And the real fault happened, there's a transformer protection sitting here. Now the transformer protection really has no business doing anything because there was a fault, current was very small due to this load. But what happened, transformer protection was wired to trip this breaker. Why to trip this breaker? Because this transformer, when the transformer has a fault, you need to connect the resource, connect all generators. You need to connect this disconnect, you need to connect this, you need to open this breaker and this breaker. For a transformer fault, you need to open these breakers. Although these two breakers are open, the transformer protection trips into these breakers and opens this breaker and killed all microgrid. So since then we can become smart. We say if these two breakers are open, we don't need to open this. We can put a new logic, but that logic was not there. We could have had a logic. If these two breakers are open, let's not open this breaker. So, but that was not the logic. So that's the fault and that mistake happened. And look at this, what happened. Basically, these are the fault records, not these are the record from this side and there's a record from this side. So record from low voltage side, the fault record from low voltage side, and the fault record from high voltage side. Actually, it was a face-to-face fault which evolved into three-phase fault. And look at how much uneven distortion in this high voltage side. We did not know about this distortion. Only this fault record told us about this distortion. Why there was a lot of third harmonic here. What we discovered, after this fault, this capacitor was tuning the system. There's a system connected here. The capacitor was tuning third harmonic. They were sucking up. They were forming a third harmonic filter. They were not filtered capacitors. They were purely power factor capacitors. They were power factor capacitor for the station. But they were also acting like a third harmonic filter. So that's something we learned it afterwards. Now the another incident happened. We are operating as a microgrid. Again, operating as a microgrid, and there was a microgrid. We are operating as microgrid only with IPP1. Only one. These two IPPs were not connected. Only IPP1 was operating a microgrid, supplying all three feeders. And for some reason, there was some problem in a plant. One of the generator tripped. So one of the generator tripped, alarm came. One of the generator tripped and alarm came. But this alarm was incorrectly wired. This alarm was incorrectly wired, actually. This wire was incorrectly wired and it tripped another generator. sorry, I think sorry, my mistake. In this case, all three generators were connected, and one of the generators tripped, and an alarm came. But this alarm wire was incorrectly connected, and it tripped a generator. It tripped one of the generators. As a result, when the generator tripped, whole frequency started to collapse, and that's what it is showing. Because of incorrect wire, we tripped the full master plant. Full master plant trip. Now we are not able to sustain. Once the master plant tripped, we were not able to sustain the plant, the station load. Frequency started to decay and eventually became 53, and it tripped, and it caused a trip, and at this point the breaker opened. And so basically, when the master plant tripped, other two generators were supporting the frequency, but at 53 hertz, we caused an instantaneous trip and disconnected. So that's for the other case. So that's it. Basically, I'm coming to my conclusions. The conclusion is distribution energy resources connections in the distribution system introduces bidirectional flows, and that bidirectional flow is not safe if we don't upgrade system protections to a system protection. But if we do system protections like a transmission system, it may not be viable. The distributed energy resources become unviable. So 2-to-1 rule can optimize protection upgrades without compromising the safety and taking into account the size of a distributed generator. Basically, the larger the generator, more upgrade. Smaller the generator, lesser upgrade. Now, distribution resources can shape the peak, basically defer the cost of capital investment for the capacity reasons. They can also improve reliability by permitting by DR to operate in microgrid. And high penetration of inverters can compromise negative sequence protection relay. That's a big challenge our industry is facing, for which, again, I did not talk about grid codes. New grid codes are being introduced, forcing IPRs for inverter sources to supply negative sequence current so that the reliable protection decisions can be made. That concludes my tutorial. I'm happy to take questions. And so, please.
Thank you, sir. Thank you very much for such an insightful lecture. And I'm pretty sure that everyone must have enjoyed this amazing presentation. Now, Professor Nagpal, we do have certain questions that came to us during the presentation. So the first question is from Mr. Atul. He's asking, can 51R sectionizers also store multiple settings like the relays?
Yes, it can. It is for effective purpose. It is a microprocessor-based device, and can, depending on make and supplier, yes, they also come with multiple setting groups. That's correct.
Okay, thank you, sir. So another question came to me is from Mr. Avinash. He is asking, as microgrid is highly unbalanced, are there sequence components are circulating all the times? If yes, how to do phase balancing in the practical cases?
So microgrid, for example, a microgrid formed on a station base will be more or less same as of today distribution station. Distribution stations are designed to have about 30-40% unbalance. In a microgrid, what is the problem in microgrid? That all unbalanced current is going to be supplied locally. All you can do a better planning, distribution planning of load distribution, and again you have to have a generator. Or if you want to operate in microgrid, you have two options. Either you do a better load balancing as a good planning process, or you put a generator which have a higher negative sequence current withstand. Zero sequence anyway comes from transformers, which have no problem with supplying a zero sequence. It's only a negative sequence. The zero sequence comes from a delta star transformer. And delta transformer is a static device. The zero sequence current is not an issue as long as I must correct, as long as it's not a three-legged transformer. A three-legged transformer has a zero sequence current. That means there will be zero sequence voltage. That will cause a lot of stray flux in the tank.
Okay, thank you, sir. So there's another question again from the Mr. Avinash. He is asking, is two setting groups enough to protect? One for the grid connected mode and another for the islanded mode of the operations.
Okay. The examples which I presented to you are realistic microgrid. Obviously, if your microgrid is very meshed and then you will need, see that it is not only two setting groups. How do you change the setting groups too? Depending on sources. So it could become a what you call adaptive protection. Either you use a setting groups or use adaptive protection. It will depend on topology of a microgrid, how many setting groups you need. But the more the setting groups, the complex is the logic of selection of setting groups. Complex of the studies. You know, the adoption of microgrid to setting group becomes complex. So the system we had as a relatively simple, the two were enough. Obviously, you had a more complex system, you need more. But adoption will become equally challenging. So I think that's the point.
Thank you, sir. So there's another question from Mr. Atul. He is curious, do relay changes their setting automatically or the manually? If it is automatic, what is the logic? Do we need to install any extra integrated devices?
I think this is a very good question, an excellent question. For microgrid, the one microgrid I mentioned, as I mentioned, it was not intended to be a planned microgrid, unplanned microgrid. It was intended to be planned microgrid. That means the setting groups are manually changed. In order to do an automatic setting group, all we needed is a signal, a communication SCADA signal for a transition. And for two setting groups, all we needed a two bus breaker status. If those two bus breakers are open, then we can switch. Actually, no. It can be a complex, it can be a simple logic. It really depends on the network. In our case, it's a plant, so we do manually. But if it's an unplanned, if you want to do automatic change, you will need a status of those two breakers, what I mentioned, and all the breakers in the transmission path. If any time transmission path is open, you need to switch a group. So therefore, you need it. Automatic transition requires in a utility system becomes a very challenging communication network problem. If you are doing in like a building in a very close knit area where you can exchange signal on what they call 61850 or easier. I think my answer is the same as the previous question. Is the logic to do a transition? It all depends on system topology.
Okay, thank you, sir. So, sir, there's two more questions. The one is from Mr. Sunil Moria. He is asking, as microgrid can be formed by using either conventional distribution lines or the cables, what is the feasible fault resistance range for both, and how they are going to affect the protection scheme?
Obviously, if they're cable, the fault resistance is very low, almost nothing. You can neglect like a phase fault. But I did not discuss one big problem with cable, resonance problem. I'm just going to go back to my slide. The microgrid with cables have obviously if they're formed by conventional sources, they have a resonance problem. If they're formed by inverter resources, that problem does not exist. If microgrid is formed by a cable, with a conventional source, I'm just going to let me. In a microgrid, if happens to be cable, if this is a cable, if this is a cable, it will have a lot of capacitance. And this source, a weak source, it's an inductive weak source. Conventional generators are inductive source. They have inductive impedance. This inductive impedance of a weak source can form a resonance circuit with a capacitor. It can form a near 60 Hz resonance capacitor. And that can cause a problem during faults and microgrid situation. However, when you have inverter-based resources, they are not inductive, then the resonance problem is not there. So, if you have a cable, the protection desensitization is not a big issue because the fault resistance is low. As long as you have an IBR, cables are not. If you have inverter resources, cables are not a problem. But if your microgrid is formed by a conventional generator, synchronous generator, which has an inductive source, you have to look for another issue. Will it form as near 6-year resonance? Actually, that is in quite detail in my paper.
Okay. I'm sure Mr. Sunil can refer your papers, and if they have any further follow-up question, they can mail you directly. Now, the last question is from Mr. Veres. He's asking, can conventional transformer, the DTRs, at low voltage level, can work with the reverse power flow from DERs?
Absolutely. The transformer has no problem. You're talking this transformer, am I right? Distribution.
Yes, sir. Yes, sir. Yes, sir.
So the question is, if I understand, can it work properly in a reverse? Absolutely. Transformer has no problem for a power flow either way, other way. It's not a generator. Generator cannot work with a reverse power flow. If there's a diesel generator, that will explode. And if it is a what they call Francis turbine, I think Pelton turbine. I believe Pelton turbine. If there's a reverse power flow, it will act like a helicopter, and it will go up like a it will get out of its foundation.
Okay.
But transformer is not a generator. Transformer can work with a forward. But I think there's an important question. The important question is trap changes. The voltage regulators. They have to be programmed for reverse power flow. They have to be reprogrammed. They have to be programmed for bidirectional. So that voltage control has to be programmed for bidirectional power. That causes tap changers cause a problem, not the transformer.
Okay. So there's one more question just popped up from Atul. It looks like a follow-up question. He's asking, can Saxoniders works on their own? If yes, can we install directional unit with them?
I didn't get the question. Could you please repeat it?
He's asking, can the Saxoniders work on their own? And if yes, sir. And if yes, can we install directional unit with them?
Absolutely. As I said, sectionalizer is as good as a protection relay. Modern. Old days they were not. Today, electronic. Let me just qualify. Modern electronic sectionalizer have all the features of modern relays. They can, in fact, they have a built-in PT. They have built-in CT, built-in PT. They can be programmed as directional devices. The only challenge is if they left isolated, disconnected from the electric system, their battery can get discharged. That's all.
Okay.
Thank you. As the power comes, the battery can get charged as long as power does not come with a fault. You don't restore a line with a fault, they will not after extended outage, long time outage, they may not able to clear a fault when you pick up a line with a fault. That's it.
Okay. Thank you, sir. Thank you, sir, for answering all these questions and for such a great presentation. And it was really a pleasure to have you with us. Now, unfortunately, this being a COVID time, we cannot felicitate you with in person. So, Mr. Chavan, maybe can we do some virtual thing? Yes. So, sir, we would like to thank you. We would like to appreciate for your contribution to make this para session a very knowledgeable session. I'm pretty sure most of the protection people who are working in the area of protection, they have enjoyed this presentation because I can see so many questions are flooding up on my own screen. So on the behalf of whole Para 2020 team, I would like to thank you for joining us today and giving us such intellectual talk. So
I'd like to express my thank you for inviting me. Actually, I know I was looking for the chat one so that I could answer questions. Anyway, first I want to thank you for inviting me. I do want to please my former colleague and my friend, Dr. Srivastava with IIT Kanpur. Please pass my regards to him.
Sure, sir. Sure.
I think Professor Ankush Sharma.
Yes, sir. He is also here.
Yeah, I please communicate my regards to him. And I think we call him a big brother. What's his name? Our from East Bengal, our colleague.
Professor Chakravarti or Professor Singh?
I think Ankush knows his name.
Okay, sure, sure.
I just the name slipped out of my mind, but I think please pass my regards to Professor Srivastava as well as Ankush. And
sure, sir. Sure, sir. Sure. So, sir, with your permission, we would like to conclude the session.
Thank you very much, and it was my honor and pleasure. And once again, my apology for mixing up the day. For some reason, I thought it is tomorrow.
It's fine, sir. And we just like to sorry. I mean, it's already 11, no, not 11, maybe 11 at your place. So I'm sorry for that. We wanted.
Okay, it's 10:30. It's time to watch some TV.
Okay.
Good night.
Okay.
Good day, everyone.
Good night, sir. Yeah. Have a good night, sir.
Bye.
Sure. Thank you. So for the participant, we just like to inform you that there's another session lined up of the para, the last session at the 5 p.m. today. Thank you, sir.
Thank you.